Hope you guys had a nice weekend. We're going to start product and quotient rule. This is going to be the last topic before our quiz. So your quiz will cover power rule, particle motion, and product and quotient rule. Uh, we can start our quiz review tomorrow. On Wednesday, I want to start the next section, which is chain rule, but this will not be on your quiz. But this kind of gives you an extra day to study. We can also have some time at the end to do some review, and then your quiz will be on Thursday. Okay, so page 35 in your packet. So before I forget, before I forget, so if you ever have to leave the classroom and you need to go to the restroom, that's fine. You can just go without asking for permission. But if you can, just always close the door behind you. We just need to have the door always closed at all times. Last session, so. So product rule is a formula used to find the derivative of products of two or more functions. We talked about how with power rule that we can't do power rule unless all the parentheses are resolved, right? We have to expand everything out. Well, this will allow us to keep the terms in our parentheses. But if we do that, we have to go through something called product rule. So product rule is where I want to find the derivative of two different functions that happen to be multiplied together. It's not quite as simple as just saying f prime times g prime. There's a little bit more to it because they're connected in ways. These two terms are connected in ways that may not be as apparent. So there's a derivative called rule called product rule that can handle when two terms are being multiplied. So essentially, they are going to involve f prime and g prime, but they're going to have to follow this pattern. So the pattern is f prime of x times g of x plus f of x times g prime. Sorry, I have my prime in the slightly wrong place there. It should be g prime like this. All right, so it's f prime g plus f g prime. And we're going to say it like this, f prime g plus f g. So they're basically essentially taking turns being the derivative, and then we have a plus between those two terms. All right, let's practice seeing what that derivative, how we can apply that derivative rule. So let's say we have a function y equals 3x minus 2x squared times 5 plus 4x. If we wanted to, we could expand this out and rely on power rule, which is perfectly fine. But we're going to practice applying product rule. So whatever comes first, I'm going to call that f. Whatever comes second, I'm going to call that g function. And I'm just going to have them take turns and follow the rule that we've built above. So I'm going to kind of make it obvious in terms of what we're going to do here. So the first part is going to be f prime. The second part is going to be g. And then back to f, and then g prime. So f prime means I want to find the derivative of this expression. G means I want to keep the original g function. F means I want to keep the original f. And g prime means I want to find the derivative of this piece and put it in this space. Okay, let's see if we can go through this together here. F prime, what's the derivative of 3x minus 2x squared? That's why 3x becomes just 3. 2x squared becomes Minus 4x, yep. So it's going to be 3 minus 4x. Okay. Took care of the f prime. Now the g function means I'm just going to pull that expression down. I'm not going to make any changes to it. And then back to f, I'm going to keep the original f function. Not going to make any changes to that. And then g prime. G prime is the derivative of 5 plus 4x. What's the derivative there? Just 4. Yeah, the 5 goes away, just left with 4. So this is our derivative function. It's a little bit more than just saying, sometimes like that. See, students want to do this. They just want to say, oh, f prime times g prime, and let that be done with it. It's a little bit more than that. So we have to make sure that we keep all those pieces. We could pull all this out and let that be y prime, but for now, we're just going to leave it in this form. The more important step is, can we get to the derivative? And again, a derivative is just a slope formula for whatever this curve looks like. Whatever this curve looks like, this y prime is doing the job of describing how the slope is changing at every single point on this curve. A quotient rule, similar idea. Quotient rule is formula for finding derivatives of functions that is the quotient of two other functions. So if I want to divide one expression by another, I'm going to go through what we call quotient rule. Now, if you look at quotient rule, it feels a lot like product rule in terms of the formula. There is still this f prime g and f g prime. The only difference is that there's a minus sign in between, and we have to divide by g of x squared. So we have to divide by the entire denominator squared. So if you memorize product rule, then you've memorized half of quotient rule. We just have to make a slight adjustment with a plus and minus, and then there's always a denominator portion for quotient rule. I think that's the piece that students miss the most about, or the mistake that comes most often with quotient rule is forgetting that there's a g of x squared. So we're on page 35. Okay, so example 2, we have 3x minus 2x squared all over 5 plus 4x. Notice that these are two different expressions. They're being divided by one another. So we're going to say, call this portion f and call this portion g. So f prime g minus f g prime all over g squared. So I'm going to build out what I want to put in place before I actually do it. F prime times g minus f times g prime all over g squared. Same process, f prime. We just take the derivative of the numerator portion. And then the way I do it is, whatever I see first, whatever I see up top is my f, whatever I see below is my g. Same thing here. Whatever I see first for product rule, I'm going to call it f. Whatever I see second is g. You don't have to, but to me, that just feels more convenience if we're always just doing the same things every time. Okay, f prime. So this becomes 3 minus 4x times g. G is just that denominator portion. F is the original top portion. G prime, the derivative of that denominator portion, that 5 plus 4x becomes just 4, all over denominator squared. The quotient rule is a little messy. Sometimes there's no way around it, especially if there's more than one term in the denominator. We can't split this up into multiple fractions like what we did last week. But if there's more than two terms or there's more than one term, we're kind of stuck going through a quotient rule. Right now, I'm not going to worry about the cleanup, but if we were to clean up, you would FOIL and expand this out. And then if you can, you will take a GCF, you can take a GCF out and try to reduce. But a lot of times the denominator cannot reduce. We got to be careful here that this is what I see some students do. They want to cancel the 5 plus 4x out. But what's wrong with that step? Why can we not do that? Yeah, that's being subtracted. So that minus sign is causing these to be connected in ways that we can't just cancel out. Unless we can factor a GCF out, we can't take this out. Now, let's say there was nothing here. If there was no minus all this term, if this is just this over this, if there was no subtraction addition that's impacting that parentheses, then we can safely take these out. But as soon as there's multiple terms separated by addition or subtraction, we're kind of stuck in this form. We cannot just cancel out. It's not the same thing. So I think the three, I would say three most common mistakes with quotient rule. One is forgetting that there's a denominator squared. Second is canceling out where you're not supposed to. And third, I see some students apply quotient rule incorrectly, and they say, well, here's my y function. I'll just do power rule above and below, and I'll say y prime is equal to 3 minus 4x over 4, so much faster. But this is not the same thing. You cannot just take the numerator denominator derivative. Now, if these were separated, if these were completely separate, and they were being subtracted or added by one another, they're not divided or multiplied, then you can definitely do that. But the fact that they're divided, we cannot find the derivative just using power rule alone and put them over each other and call that the derivative. We have to go through this process. Okay, let's go to the back. Okay, higher order derivatives. We talked about this briefly where with particle motion, where we were able to make our way down to the second derivative. Um, but we could go further. We could go into the third, the fourth, and fifth derivative. But if you're asked to do that, it'll be relatively simple because it'll just be nice power rule where you're just going to take the derivative of the previous function and just go down the chain there. So let's see if we can try that. Can we find y prime? And then to find y double prime, we just treat the previous problem or treat what we see as the original problem and just keep on going through the derivative process. So y prime here, we get 10x to the fourth plus 4x cubed minus 9x squared minus 16x. And what about the last two terms here? 10x becomes 10. And then the negative 12 becomes 0. Okay. All right, keep going. That's the first derivative. Second derivative. Negative 16x becomes just negative 16, and the 10 goes to 0. Now, let's say, what prediction can we make, assuming that we're always starting with a nice integer or a nice positive integer exponent? what's going to happen eventually if we take enough derivatives? Do you notice any pattern with these terms here? Well, how many terms did we start with? 1, 2, 3, 4, 5, 6. And then what happens next? 1, 2, 3, 4, 5. What's going to happen if we keep finding the derivatives of these terms here? Or what do you expect to happen with the degrees each time we find a derivative? They're going to keep doing what? Decreasing, right? And eventually, what's going to happen? Let's say we were making our way down to the fifth or sixth derivative. Eventually, all these terms will do what? Yeah, there's a zero out, right? They will eventually zero out. So that's also something that is a nice property with power rule is that each derivative, I mean, assuming that we're starting with a positive integer, it's always going to get simpler and simpler, and the derivatives sometimes can get more complex for different types of functions, but for polynomials at least, the derivatives are nice and easy and clean. Okay, so we keep going here. We get 120 x squared plus 24x minus 18, and the last one, 240x plus 1. So every time our degree will fall by 1, and eventually it'll turn into a degree 1 constant and then 0 out. There are numerous notations for derivatives. For first derivative, you might see a notation like f prime or g prime or y prime or dy dx. Dy dx is basically saying this means find the derivative of my dependent variable y with respect to my independent variable x. So that dy dx, it may look more complicated, but it's also more descriptive because it tells you, it indicates to you what your dependent variable is and what your independent variable is. Usually, our dependent variable is y, our independent variable is x. That's where most of your problems will come into play. But sometimes your independent variable is a t or other variables. And then looking at this, you can tell that whatever is up top is basically your dependent or your, excuse me, whatever you see up top is basically your y variable, and whatever you see below is basically your x variable. So if it's like dr ds, then s is your independent and r is your dependent. Or if you see dy over dt, then that tells you, okay, time t is my independent variable, and whatever up here is my dependent variable. Notation for second derivative, you may see f double prime, y double prime of x, y double prime, d2y over dx2. This is the notation for second derivative. Okay? This doesn't mean I'm going to take my derivative and square it. The 2 indicates the second derivative. It doesn't mean that we're squaring anything. And we're not going to see third derivative much, but you can imagine just follow the pattern to build the third derivative notation, f triple prime of x, y triple prime, and following the same pattern, you can find to notate the third derivative, d3y over dx3. Okay, let's see. So that's basically today's lesson. I would like to see if we can maybe get started with our quiz review and just kind of begin to tackle some of the particle motion, the practice that we may want to have with particle motion and power rule, since those are the main major topics. So if you guys turn to page 43, we're going to work through particle motion problem. Okay, so 43 says, we know that typically the order is position, velocity, acceleration. I call it PVA. Um, position is the original function, the derivative is velocity, and the second derivative is acceleration. But here, we're already at the velocity level, so we're only going to be dealing with velocity and acceleration. We don't know how to go back up the chain yet. We'll learn that for second semester, but first semester, we can just go down the chain. So if we're starting at position, we can get to velocity and acceleration, but if I give you velocity, you only know how to get to acceleration. We don't know yet how to go back up. Here it says velocity of a function is described by the function v of t equals 1/3 t cubed minus 2t squared plus 3t plus 2. So this is describing the velocity at any moment in time. And it says, find the time when acceleration is 0. So we first have to figure out how to get to acceleration, right? So how do we get to acceleration from the velocity function? Just find the what? Derivative, yep. So acceleration equals, we go through power rule, so we bring that 3 down in front. 3 times 1/3 is just 1, so we get t squared minus 4t plus 3. And that 2 goes away to a 0. So it says find the time when acceleration is 0. So what can we do? Take acceleration and do what with it? That equal to 0, right? We're trying to find the time when acceleration is 0. We don't want to put 0 in for t because that wouldn't fit what the problem is asking. We want to find the unknown time at when acceleration hits 0. So we'll set 0 for acceleration. Now this we can factor, right? Binomial factoring multiplies to be 3, adds it to be -4. Solve for t, we get t equals 3 and t equals 1. So now that we have the moments in time when acceleration is 0, we can find the velocity when acceleration is 0. So we can plug 1 and 3 back into velocity to find the velocity at those moments in time. So 1/3 in for, sorry, 3 in for all the t values. 1/3 3 cubed minus 2 times 3 squared plus 3 times 3 plus 2 ends up giving me 9 minus 18 plus 9 plus 2, which is 2. And then velocity at 1 second, or when velocity at t equals 1 is 1/3 minus 3. Sorry, 1/3 minus 2 plus 3 plus 2, which is 10/3. Okay, questions so far? All right, number two. The position function is moving in a straight line, x of t. So this is a particle motion. This object is only doing one of three things. It's either moving to the right, it's moving left, or it's standing still, or maintaining in the still location. Now, this is only for t is greater than 0. So we do have a restriction. We're only looking at t values greater than 0, only positive t values. So part A says, when is a particle at rest? So what's another way of saying it? Particle at rest means what? Velocity is 0. So we need to make that connection that rest is related to velocity, but it is when velocity is 0. So we just have to set v of t equal to 0 and solve for t, right? But to get to velocity, we first have to do what? Find the, we're sitting at the position level, right? So we need to find the what? Derivative, right? Yeah. So let's try that. Find v of t first. Okay, 24t becomes 24. The constant 2 will go away to the 0. Set equal to 0. Again, I got a factor. So GCF first. Multiplies to be 8, adds it to be negative 6. Negative 2 and negative 4, and now we can solve for t. There's a 3 sitting out here, but if we set 3 equal to 0, that's not going to make sense, so we can ignore any coefficients. We only care about solving for the variables. So t equals, we set t minus 4 equal to 0. We set t minus 2 equal to 0. We get t equals 2, and we get t equals 4. Now, to get to part B and C says, during what time interval is a particle moving to the left, or sorry, moving to the right, moving to the left? We're going to create a number line, a velocity number line. If we create a number line, we can find out when the interval is positive or negative, and positive would mean moving right, negative would mean moving left. So we're going to first create a velocity sign line. We can have the sign line in front of us, then we can just read it to determine the intervals when it's moving left and moving right. So here's my velocity sign line. We have most of the information that we need. We need the critical points is where the velocity is 0. So this is when, so we can say 2 and 4. We can also include 0. Why is that? Why can we also include 0 on our number line? That's our starting, right? That's our starting value. We know that we can't have anything less than 0, so we know 0 is going to be a starting point for this problem. So we have 3 separate intervals to test. We know that between 0 and 2, this particle is going to only move in the same direction, either left or right, and then it's going to stop. And then from 2 to 4, it may change direction, it may not. It may keep going the same direction. And then from 4 to infinity, it's also going to be consistently moving in the same direction. So to find test values to plug in, and then to find out the behavior in each of these intervals. So I'm going to choose easy numbers that are as small as possible. So between 0 and 2, I'm forced to just choose 1. That's the easy number there. Between 2 and 4, I'll choose 3 to test. And between 4 to infinity, I'll choose 5. Anything closest to 0 is going to be the easier number. And I'm going to plug this into, guess what I'm going to plug these into? Am I plugging into the velocity or into the position? The 1, 3, and 5. the question that, common question that students ask, where do we plug these numbers into? What do you guys think? Into the velocity. We want to find the direction of motion. If we plug 1, 3, and 5 into the position, we'll be able to find out where the object is, but we're not going to know which direction it's moving. So we're going to plug it into the velocity function. Now, there's different variations here, right? You have the original velocity, you have a semi-factored, and you got the fully factored. My suggestion is plug it into the fully factored one. You won't have a calculator, so this is the fastest way to get to the sign without having to do a bunch of calculations. So if I plug 1 in for t, 1 minus 4 is negative. 1 minus 2 is also negative. 2 negatives makes positive, so I know that that positive indicates I'm moving right for that first interval. Plug 3 in for t. 3 minus 4, that's negative. 3 minus 2, that's positive. Negative times positive is negative, so it's going to change direction, turn around, and start moving to the left for the next 2 seconds. And then plug in 5 to get a test or to find out what's happening in this interval here. Plug 5 in for t. 5 minus 4 is positive. 5 minus 2 is positive. 2 positive makes positive, so positive. So let me kind of give you a visual in terms of what's happening here. When the timer starts, this particle is going to start moving right for 2 seconds. After 2 seconds, it's going to stop, turn around, move left for another 2 seconds, and then turn around and move right from 4 to infinity. Now, as soon as you test the 1, 3, and 5, you want to make sure that you don't use those numbers again. Those will not show up in any of your interval notation. You're just going to use 0, 2, 4, and infinity for any statements about moving left and moving right. Those test numbers are just to get the signs. After you get those signs, those numbers are not going to be used for anything else in the problem. So part B, during what time interval is the particle moving right? All we need to do is to read this tape or read this sign line for our answer. So when is the particle moving to the right? From where to where? From 0 to 2. And 4 to infinity. Okay. I'm going to ask you for reasoning on the quiz. So you're going to say because v of t is greater than 0. Think during what time interval is the particle moving to the left? To the 4. The reasoning is because velocity is less than 0. So given the function x over x minus 3, find the equation of the tangent line. So we need to find order pair, find the slope from the derivative, and then point slope form. So order pair, that's pretty straightforward. I can just plug that 4 in for x to get my order pair. Now to get to the derivative, what process do we have to go through to find the derivative? Can I just do power rule and say x becomes 1, x minus 3 is 1, so just 1 over 1? What did we learn that we have to go through if two terms are being divided by each other? What rule do we have to go through to find the derivative? Yeah, quotient rule. Now, tomorrow I'll talk about when we can avoid quotient rule. Basically, if there's only one term in the denominator, we can split up into individual fractions. But as soon as you have multiple terms added or subtracted in the denominator, you're kind of stuck. You have to go through quotient rule. So quotient rule is f prime g minus f g prime. all over g squared. So f prime equals. Now there's a repeat variable here. So this f and f prime is different from the f and f prime within quotient rule. So okay, f prime, that's going to be the numerator portion. So x's derivative is just 1. G function, no changes. Back to f. And then g prime, the derivative of x minus 3 is just 1, all over denominator squared. So now I have my slope formula. I can plug 4 in to get the slope. Let me clean up my f prime first. So here's my f prime. This is how I'm going to get the slope of this curve at a particular point. So I can plug 4 into my slope formula to get to my slope. So f prime of 4 so negative 3 over 1 squared is negative 3 over 1, which is negative 3. So I have my order pair is 4, 4. I have my slope, which is negative 3. And now point slope form. Okay, part B says find the equation of the tangent line to the curve where the slope is equal to negative 3/4. So we don't have to know what the graph looks like, but just to kind of give you a an idea of what we're trying to do here. Let's say the graph looks something like this. Trying to figure out where on this graph is there a slope equal to negative 3/4. So you can kind of maybe imagine there's maybe 2 places that can experience that negative slope of negative 3/4. So we're basically trying to find the equation of these 2 lines. But first, we have to locate the order pair where this slope is going to be exactly negative 3/4. Well, anytime we're talking about slope, we know that we're referring to the derivative. So how can we involve the negative 3/4 and the derivative to get to the location that we're looking for? How can we involve that negative 3/4 with this derivative function to get to the location? Put a negative 3/4 in for what? Can I put it into the x location of the derivative? Or should I put it into the f prime variable? Yes, think. So is this a slope value or is this a location value? Slope. So this should go where? F prime. Yeah. So remember, the f prime we can ask it for 2 different pieces of information. We can give it a location and ask for the slope, or we can give it the slope and turn around and ask for a location, right? So it can go both ways. So in this case, it's more helpful if we put that -3/4 into the f prime location and work backwards and solve for x. When we solve for x, we can find these particular places on the curve where the graph is experiencing these particular -3/4 slope. So let me write that f prime. So -3/4 is my slope that I'm looking for, and then I can solve for x here. I'm going to FOIL this out. I'm going to cross multiply, get rid of my fractions here. And there's no shortcut to this. We really, well, I guess we could divide both sides by -3 here. I think that maybe it'll feel faster. So we can say x minus 3 is equal to plus or minus square root of 4, which is 2. So x minus 3 equals plus or minus 2. Just be careful. We got to do this twice. We got to say x minus 3 equals 2, x minus 3 equals -2, and then we can solve. We can't say plus 3 and just make it plus or minus 5. Not quite the same. So we can say x minus 3 is equal to 2, or we can say x minus 3 is equal to -2. Find those locations separately. So we get x equals 5, and we get x equals 1. So we can expect two different locations where the graph is experiencing a negative slope of 3/4. So now I can plug the 1 and 5. How can I find the order pair? Back into the what? Into the original function, right? So I'm going to say f of 5. That's going to give me 5/2. And f of 1 will be -1/2. So I have two locations that both share the same slope of -3/4. So then independently, I'll write the tangent line equations for both these locations. Okay, check your calendar for your homework. And tomorrow we'll continue with our quiz review. We'll have a full class period to do quiz review. Your quiz is going to be on Thursday. All right, come get your phone. There it is, guys. Did we have a question? Yes, yeah, oh. We have two on Texas. Yeah, that's all. Yeah. Yeah. I wasn't here Friday. Yeah, but like, I can't go anymore. I don't know. Maybe I'm cooking. No, I'm not cooking at all. I will be getting a cooking. You did. Like I did you get up like 7 and make me have to stay tested. Well, actually, last week, but. Well, technically, it was a well, yeah, but that was the whole thing. You think you'll do the same verdict for the test, like, if I get a 20 on the test, I'll get like a 70? Maybe. Hopefully. Hopefully. What happened? Yeah. Maybe you'll put a displacement question and you'll hear like I don't know what displacement is. You the area under velocity. Oh, I think they're both. I don't know how to do that. You find the area. I'm not good at that. I can't like stuff, but I can't do like basically this time and I lost my I thought I was talking and I can't manage No, you have to. Yes, I'll do that back. Okay.
Congratulations to the flag of the United States of America and to the republic for which it stands, one nation under God, indivisible, with liberty and justice for all. Please pause for a moment of reflection. Thank you.
But I can love it. And I talked to one that I wanted. So big choke, definitely out. But wow, I